In the previous section, we studied the production of images by mirrors. Optical images can also be created through refraction by lenses. A lens is simply a piece of glass, plastic, or other clear material that is curved on one or both faces. The curves cause light rays passing through the lens to bend. The bending of light by a thin lens can be described by fairly simple equations. The bending by very thick lenses, however, is very complicated. A thin lens is referred to as thin because, compared to its diameter, it is very thin. Light rays passing through a thin lens behave in a specific fashion with regards to the focal points of the lens. One kind of thin lens is a converging thin lens. When light rays that are parallel to the axis of a converging thin lens strike the lens surface, they are bent by the lens in such a way that they converge and focus on the far side of the lens. Light rays that pass through a focal point before striking the converging lens are deflected by the lens to a path parallel to the lens axis. In a diverging thin lens, the roles of the two focal points are reversed. When light rays that are parallel to the lens axis pass through the lens, they are deflected to diverge as if the light came directly from the first focus. Light rays that initially are directed towards the far focus are turned outward by the lens and move on parallel to the lens axis. Converging lenses are often convex on both sides. That is, they curve outward on both sides. However, one side can be flat, or even concave, as long as the lenses are thicker in the middle than at the edges. This thickness ensures that the convex side dominates the deflection of light rays. Diverging lenses are often concave on both sides, giving them an hourglass shape. However, one side can be flat, or even convex, as long as the lenses are thinner in the middle than at the edges. This central thinness ensures that the concave side dominates the deflection of light rays. Now that we know what features constitute a converging or a diverging lens, what determines the value of the focal length f? What do you suppose will happen to the focal length of this lens if we increase the curvature of the lens? Correct. As the curvature increases and the lens gets thicker, the focal length decreases. This is because the light hits the lens at a greater angle and, therefore, refracts more. This is true for both converging and diverging lenses. Now suppose the lens is glass, with an index of refraction of n equals 1.5, and we immerse the lens in water, with n equals 1.3. What happens to the focal length? Correct. The focal length increases. This is because the difference between the index of refraction of the lens and that of the surrounding medium is less than in air, and as a result, the light rays refract less. In general, lenses with more curvature bend light more and have shorter focal lengths. In addition, the greater the difference between the index of refraction of the lens and that of the surrounding medium, the shorter the focal length.